Hi, 505 team. I'm going to go through this presentation pretty quickly, but you will have these slides available to study on your own later. So our key words: what is computation? What is a computer? There are some connected questions for getting at these. What is computation? Why are we using binary electronics coupled with binary logic and base 2 binary number system for encoding and processing computations? What makes a computer a computer? Why is it better to use the term computer system rather than computer as an object? Well, you may know that English and many other European languages, computation and computing originally meant calculating, reckoning with numbers. It comes from the Latin word computo, computare, meaning to calculate. So a computer was initially the name of a job title, someone who was skilled in doing calculations, not a machine. In fact, here's a cool ad from 1892. If you wanted to be a computer, you could take the exam in Washington. You could get $1,000 or $1,400 a year, but you had to know algebra, geometry, trigonometry, and astronomy. Well, here's a computer room in 1910, full of computers doing their work. In the 1930s, when Alan Turing wrote his first mathematical papers, a computer still meant the person doing the calculations. The word computer gradually shifted to the term for the calculating machine itself in the 40s and 50s, with the designs for the big room size number crunching computers, as we call them, being developed in the US and in the UK. But these giant calculating machines were designed for specialists, trained mathematicians, engineers, and scientists, and not ordinary people. But modern computing is not a story about machines, as we often see, like the images above, but about designs for implementing human symbolic thought, delegated to physical electronic structures for automating symbolic processes that we can represent in digital form. Let's go to the real story. Well, it didn't only all begin with Charles Babbage, the guy who invented the difference engine and then the analytical engine in the 19th century, but Dasgupta makes a great point, so let's read. I've highlighted some terms here that you can pay attention to. So we'll see that the domain of computation actually comprises symbols, not just numbers in math, right? The act of computation is then symbol processing, the manipulation and transformation of symbols. Numbers are just one kind of symbol. Calculating is just one kind of symbol processing. And so the focus of automatic computation, Babbage's original dream, is whether or how this human mental activity of symbol processing can be performed by, or as we might say today, outsourced to machines with minimal human intervention. Computer science is the science of automatic computation, is also the science of automatic symbol processing. Well, a little background on how we get to this concept today. Well, in the 40s and 50s, John von Neumann, who was important in the early design of computer systems and the central processing unit, discovered that when he saw binary representations in bits and how they could work in a computer system, it could not only represent data, numbers that mean things, but executable instructions, numbers that do things. So breaking this distinction, he created the idea of the stored program computer, what we're used to today. Well, we can generalize further over this concept of numbers that do things and numbers that mean things, and talk about a digital computer system as a design for combining symbols that mean, that is, represent values or meanings, we call data, and symbols that do, symbols that perform actions over the meaning representing symbols, that is, programming code and software. Well, how did we get from computing means calculating or number crunching to computing as general symbol processing with ways to represent, i.e. compute, process, interpret, transmit all of our symbolic forms that we encode in data types in systems designed so that anyone can use them, our current concept of computing? Well, I'm going to have to glide over lots of history here just to focus on the key concepts, but you can all research how we got from there to here, but we're just going to look at the main ideas and the design principles. Well, there's an important step that you need to know getting from there to here was The work done in Doug Engelbart's research lab in the 1960s, really cool design step conceptual leap. So the basic principles about symbolic processing were expanded further in the 60s by Engelbart, who developed a lab at Stanford devoted to augmenting human intellect with a new kind of computer system, which was no longer a number crunching machine. He and his team envisioned our modern multimedia interactive graphical interface computers, and he invented the mouse, hyperlinks, and multiple windowing for output displays, everything we take for granted today. Let's look at some of the ideas that motivated him. It's really fascinating to read back to these documents in the 60s because we see the future. We see how we got from there to here. In our culture, there's recently appeared a symbol manipulation artifact, the computer, of such power that we feel certain it's going to extend man's intellect, right? And his program focused on examining this working domain viewed as a symbol manipulation system. For this application, the stereotype of the computer is only a mathematical instrument. It's too limiting. Essentially, a computer can manipulate any symbol in any describable way. So our aim is to give help in manipulating any of the concepts that the individual usefully symbolizes in his work. And mathematical concepts constitute only a limited portion of most real-life instances. Okay, if we define modern computation as symbol processing, which is based on human symbolic thought for combining two orders of symbols, remember the meaning representations and the operation representations, how do we get digital binary computers to be symbol processors? How do we get representations of symbols that mean and symbols that do into the physical structures of a computing system, and how do we make them active for doing computations? Well, this is all connected to answering why binary. Why are we using binary electronics coupled with binary logic and math? Well, electronics provide the fastest physical structures for registering and transmitting signals that we can encode for representing symbolic structures, numbers, written characters, images. But electrical current is a continuous waveform and not naturally capable of discrete representations. That's representations distinct and differentiated from each other. How can we use electricity to hold a pattern? Well, electricity is part of the electromagnetic spectrum. You know, if you see on this chart, we've developed ways to engineer and design many different slices of the spectrum, and electricity and current is on the low end, as you can see, around this 50 hertz cycles of waves and energy. Therefore, we need a designer electronics. Hey, thanks, electrical engineering information theory. That's what that's all about, by the way. Designer electronics, information theory, to impose a shape, a pattern, a structure on a type of natural energy that is nothing like human logic or meaningful symbolic patterns. Okay, how? Well, the simplest electrical pattern that we can design, implement, and control is a simple switch states, you know, like an on-off switch. It's closed or open. There's presence of a voltage or absence of a voltage. Aha, a binary system. It has only two positions, two values. I wonder what we can do with that. Well, the idea goes all the way back to Samuel Morse and electrical telegraph code, the first symbolic abstraction for mapping a human sign system, that is typographic characters, onto electrical signals as switch states, on, off. That's patterns of electrical pulses can equal patterns of written symbols. Great quote from Morse, recalling how he originally had this idea way back in 1832, right? He saw experiments with electricity, and it occurred to me, he says, that if the presence of electricity could be made visible in any desired part of the circuit, it would not be difficult to construct a system of signs by which intelligence could be instantaneously transmitted. I planned a system of signs and an apparatus to carry it into effect. Actually, there's the secret, right? The presence of electricity made visible in any desired part of the circuit. That's what we're still doing. And Morse code, which spread through the world internationally really quickly, it's still in use today, was like a proto-binary system, dot, dash, on, off, presence, absence, right? And binary systems for typographic characters soon followed, all the way to our present day Unicode, which is behind every form of text we use today. Okay, how do we get both levels of representations, that's the symbols that mean and do, into the binary architecture? And then how do we activate them to do computations? Well, the technique for shaping binary electronics into patterns of bits and bytes is motivated by what we can make two-state units mean. We can create a perfect mapping system, as it's called in math and in science, for a one-to-one correspondence between simple on and off states of electricity and human high-level symbolic systems, binary logic and the base 2 number system, which have nothing at all to do with electricity. So by imposing logical symbolic meanings and values on bits and bytes, depending on the computing context, we can make a bit mean yes, no, 1, 0, true, false, present, absent, all, nothing. But remember, there are no ones and zeros in computers. We often talk this way, and you may hear people say this. 1 and 0 are human symbols that we use for meanings and values, and we impose a correlation on the digital electronic structure to represent ones and zeros in contexts when that's what we want them to mean. So we put a sequence of bits together in groups, we get a pattern, right? Bytes. We can encode a pattern of bytes to represent our symbolic patterns, any digital data type or form of digital media. Now, binary encoding in defined data types gives us representations for all our symbolic systems. Of course, ultra-fast number crunching calculations. Program code is designed to activate the processes and use our data representations, that's the symbols that mean, as the input for the operations, the symbols that do, that go with the kind of data types we're using. Here's how it gets activated in the whole computer system. Well, if you took a course in Computer Science 101 or Digital Engineering 101, you would learn the engineering diagram symbols for logic gates, as we call them. These binary switches that enable us to combine various truth values by kinds of inputs going through a circuit and yielding an output. This is all standardized in the circuits of computing processors, and rarely does anyone ever have to think about this because it's all standardized. But note, these diagrams and truth tables are human abstract symbolic systems imposed on circuits, not properties of electricity. Today we have core processors, the CPUs, with millions of these switches that convert bit inputs to outputs over synchronized states of time, sequences of time. We have to design time to do computations as symbol processing? Well, yes. A computer program, when running in RAM memory, continues an ongoing dialogue with the operating system, with memory locations, with the processors, all those logic gates, and goes through billions of state changes per second as directed by a binary clock. Tick tock, go, stay, do, hold. Looks kind of like this. The clock pulses go through the CPU and then get communicated through the whole computer system, timing when every cell in RAM memory gets switched to a presence or an absence, and on or an off. So the program activates all these chains of different kinds of logic gates in the processors, controls all these transitions. The transitions on our data inputs and reads and writes to binary form from RAM, but it's the digital clock that makes the whole system perform synchronized state transitions to give us computations, that is, changes and transformations over states of time, and create the representations that we see. Well, here's the logical design of a CPU. You'll see diagrams like this in any computer science book. The black arrows show us how the processes flow in and out and through the CPU, and the red arrows, how the control sequences work, including the clock unit. Now, inside the arithmetical logic unit, the ALU, are all of these millions of binary logic gates, which we can use to do all kinds of things, mathematical calculations, control the flow of truth and false and presence and absence, when we want to do any kind of processing of any symbol. So at the input side, the programming code, the symbols that do, also include bytes of encoded data that are fetched from the memory units for each sequence of the process. And the outputs, they get transferred to the software levels and the user-facing levels that we see, or they can trigger actions in other things. So what's inside a chip? Well, this is a really interesting diagram of the die, it's called. That is what gets printed on the silicon, right? It's containing, all of the processing units with their logic gates, millions of processing memory units, and all those pinouts, those are those gold soldering things you see around the edge. Those are connected to the rest of the computing system. Well, if we could visualize this, visualize how a program that we're using orchestrates all these encoded bits and bytes flowing through the logic gates, performing steps in computation, and combines the symbols that mean and symbols that do, it would look kind of like this. So this is a simulation of a core processor just going through a bunch of system changes. And of course, various kinds of code that we might write on the left. But what happens is that we have a step of translating our code symbols that we understand and interpret into binary representations, right? And these are then assigned to cause physical actions in processors and memory locations in the logic flow and state transitions, that is transforming inputs to outputs. This is what happens, the visualization of when we enact symbols that do inside the system. So this whole logical structure, right, implemented physically for automating controlled sequences of input encoded symbols to output encoded symbols is what makes a computer a computer. There we have it, a snapshot, right? No magic, no mystery. It's all part of human design. So you ready to give some answers to our questions about our keywords? What is computation? Well, computation today means information processing in the sense of information transformation for all types of digitally encodable symbolic forms and the kinds of operations and interpretations that can be applied to the encoded forms, which we call data types. At the core, computation is achieved by symbol processing using a sequence of logically controlled steps. Those are represented by the symbols that do in programming code that get translated into actions to transform one state of representations of our symbols that mean into further interpreted states of representations in unlimited ways determined by human agents in dialogue with software and the whole computer system. Well, why are we using binary electronics and binary logic? We got a snapshot of that earlier, and I think you probably got the idea of this correspondence logic. It's the coolest trick we do with electricity. Binary electronics, with digital information modeled on the binary bit, is a logical, mathematical, engineering solution to a symbolic representation and symbolic processing problem. What problem? We want to use electricity. It's really fast. Even Samuel Morse knew it, right? Electricity made visible, that is present in any desired part of a circuit. But how can we make electricity hold a pattern that can represent something not electronic? That is human symbols, abstract values. Well, we impose a structure on electricity in sequences of on-off states, bits, and then assign symbolic values to the physical units. This allows us to create a perfect correspondence map for our base 2 number system and our binary, that's Boolean 2-value logic. The binary system gives us a whole unified subsystem to build on. We can build many layers on this subsystem for creating all kinds of data structures and define patterns of bytes, which are interpreted by corresponding software processes. You know them, right? Digital text, mathematical symbols operations, images, graphics, video, audio, everything we can digitize and process today. What makes a computer a computer? Well, we saw a view of that earlier. Let's recap. As we saw above, a modern digital computer is a design for a system architecture that uses 1, binary electronics and processors, memory, system clock, input and output, 2, coupled with binary logic and mathematics in processors for interpreting and moving bytes around for both orders of symbols through states and memory locations in the system. 3, for the purpose of automating symbolic processes over controlled sequences in time by transforming input encoded representations into output encoded representations interpreted by software, all the layers and kinds of software that we use. What is a computer system? And why is this a better term? Well, a digital computer system, together with all the types of digital data and media, is an architecture of subsystems designed in many levels and layers and combined together for one main purpose: to orchestrate, that's to combine, sequence, and make active symbols that mean, our data representations, and symbols that do, programming code, in automated processes for any programmable purpose. We should use the term computer system because this helps us keep the concepts for symbol processing systems in mind. Keeping the systems view in mind also helps us in de-block boxing any level of computation and components in actual computer systems that you may want to understand. Well, I hope you enjoyed this. I really enjoyed putting it together, and I really look forward to our discussion in class. See you soon.